Okay, so this is a follow-up video to one I've just done on finding the inverse of a 3 by 3 matrix. It's another way of finding the determinant, not the actual inverse itself, just the determinant. Now, numerically, it's pretty straightforward to find any determinant. It's just effectively masking rows and columns and working it out using these metrics of signs and so on, as I've just demonstrated. But there's also a set of rules you can apply to matrices to make that process a lot easier. Now, numerically, it doesn't really have much advantage, but when we start talking about algebraic matrices, it really does help. So I'm going to introduce it with a numerical matrix, the one that I've previously used. So I know the determinant, to put up here, is actually equal to -6. I'm not going to calculate that in the previous way. I'm going to calculate in a new way using the I would call rules of manipulation of matrices. So the rules are pretty straightforward. You can add any two columns or any two rows and the determinant remains unchanged. That also goes for subtraction. So you can subtract any two rows or any two columns and the determinant remains unchanged. You can also scale up any row or any column and do the same thing, so addition, subtraction, and the determinant remains unchanged. The advantages of this I'll show you shortly. So the next set of rules is if you multiply any row or any column by a constant, then the determinant will also be multiplied by that value. Okay, so same goes to division. If you multiply by the reciprocal of a constant, i.e. divide through by that constant, then the resultant determinant will also divide through by that value. So I'm going to just use these rules quite quickly to show you how I can actually simplify the process of finding the determinant of a matrix. Okay, so this is the matrix I've previously used to find its inverse, and because of that I know that the determinant of that matrix, represented by the two vertical lines, is actually equal to -6. Now, so what I'm now going to effectively do is use the matrix manipulation rules to go ahead and simplify the process of finding the determinant. So an objective really would be to try to create zeros in the elements on the bottom left, for example, or the bottom right, or whichever corner really, so that actually simplifies our calculation. So we're basically going to use the numbers we have and the rules of manipulation and try and make these zero. So how can I zero those elements? If I look at my third column and my first column, you'll notice that we have 2 and 2, -3 and -3. So if I subtract my third column from my first column, that's actually going to zero two of my elements straight away. So the determinant of A is going to be the same. Notice I'm using square brackets for the matrix and just vertical lines for the determinant. So the matrix itself is changing, but the determinant won't. So that's going to be 2 subtract 4, so that's -2. There's going to be 2 subtract 2, so let's turn that to 0. That's still -5, and that's still 2. So we're leaving this as it is. And then -3 subtract -3, that's also 0, 6, -3. Okay. So we've already got two 0 elements where we wanted the 3, so we want this one, and this one to 0. So now we want to change the 6 to 0. And again, if we look at the right-hand column, you'll notice that if I double this, remember we can double or multiply by any scalar value. If I multiply this by 2, i.e. the whole column by 2, and add it to the second column, that's going to zero that element. So remember, we're multiplying that by 2, and then we're going to be subtracting. Okay, adding, because it's a negative. Okay, so again, -2, 0, 0, that remains unchanged. So doubling this and adding it to that, 8 plus 3 is 11. Doubling that is 4, -5, so that's -1. And the whole purpose was to turn that 0. And that now becomes 4, 2, 3. Notice we haven't doubled this, we simply doubled it when we subtracted. Okay, so we've left it the same. So basically what's happened here is the determinants remain unchanged, but now when we work out the determinant, we can basically use the third row and the third column, and remember it's plus minus plus minus plus minus plus minus plus, so this remains unchanged. So the determinant of A is actually going to be equal to -3, our intersect, multiplied by the determinant of what's left here, which is -2, 11, 0, -1. And we don't have to consider these two anymore because they're zeros. So our calculation is greatly simplified. So remember, we've got a cross here, so it's going to be -2 times -1. Subtract this cross here, 11 times 0, obviously 0, and then multiply that by our -3 outside. Okay, so that's 2 multiplied by -3, which, as I predicted, would be -6. Now, again, bit of work to get to this point, and it would have been easier or just as straightforward to have calculated in the normal way. But when you come to algebraic matrices, things become a lot more problematic, and this simplification method works really well. So I'm going to do an example of that shortly.